righty. So I guess we're going to be having some fun. All right, so we're going to talk about matter today. Matter doesn't matter. Boom, roasted, Mr. P. Anyways, we're going to talk about a different topic here in Unit 2. So we're moving past density stuff. We'll still incorporate some density stuff, but we're in a new fold of the unit here. Now, as always, you shouldn't feel the need to write down every single word that I have on my board. Just kind of fill in the blanks, write down the most important things. What is matter, by the way, Mr. P? What the heck does that even mean? Anything that has a mass or a volume. Matter is anything that has mass or volume. Okay? So if it's got a mass and a volume, it's matter. If it's matter, it's got a mass and a volume. Everything is made out of matter. Okay? Everything. Everything. Laura, her mask, her hair, her clothes, her pencil, her paper, her phone, her table, her chair she's sitting on. Everything is made out of matter. The air she's breathing out right now, made out of matter. Okay? It all has mass, it all has volume. Anything you can think of. I had a really great question last period. Someone was like, oh yeah? Well, what about light? Light is matter, by the way. It does have mass. Little photons.
What's the volume of light?
The volume of the little photons, I suppose. It's hard to, you're like, wait, but light? But there are a lot of things that are matter that you don't really think of lots of times. Like, so the sound, well, sound's a little trickier. Sound definitely uses matter to travel. I'll give you that. Yes?
How do you measure air for matter?
That's a good question. I will leave it at this. The air around you, although you don't quote-unquote feel it really ever, especially when you're inside, there's not like wind or anything. But all those little molecules around you, they all take up some certain amount of space. They all have a mass to them, and so they are matter. Yeah. So air is always pressing down on you, and it's called pressure of atmospheres, all that good stuff. That's more Unit 8. But suffice it to say for now, even air, which doesn't feel like it's anything, does have mass, and it does take up space, aka has volume. Now, there are pure substances. We're going to start to draw a little tree here. I'll come back to this real quick in a moment. So we have matter up at the top, which is everything. It breaks into two parts. I will in a second. It breaks into two parts. You have pure substances on the left, okay? And so we'll come back to this tree several times. Pure substances. A pure substance is a constant composition with fixed ratios of elements. Maybe just put a fixed ratio of elements. And I'll explain what that means. I'll give you lots of visuals for what that means as well. It can't be separated by physical means, okay? So if you have a pure substance, the only way you can separate it into different pieces is if you chemically change it. But it can't be separated physically. Now there are two types of pure substances. I'll be back to the slide in a moment, a mere moment. So we're going to find that pure substances itself splits off into two. The first one we're going to talk about are elements. Now, of your Petri dishes, you guys at home can't see this, but you guys did this. Of your Petri dishes, group 2, 4, and 7, they were pure substances. Well, how do you know that, Mr. P? Hey, if I close my eyes and grab some out of this Petri dish, what will I get every single time? I will get a blue pipe cleaner. No matter what I grab, I'll get a blue pipe cleaner, okay? So no matter what I grab out of the container, if it's always the same, that means it's a pure substance. The same can be said about this Petri dish. Now I have some red beads in here and black beads, okay? But no matter what I grab out of here, if I grab a red bead, I'm going to get one red bead and one black bead, aren't I? If I grab a black bead, I'm going to get one red bead and one black bead. So this is also a pure substance, and we'll talk about that here in a moment. Elements are substances that can't be separated into simpler substances. They are as simple as you can get them. They are as simple as you can get them already. There aren't smaller pieces. They are also the building blocks of everything around you. Examples: chlorine, sulfur, sure. Here's a container of sulfur. Again, you folks at home can't see this, but it's just a little container with yellow powder in it. This is sulfur. Every single little atom in here is a sulfur atom. And you can't break them down into smaller pieces than that. Every single thing on the periodic table is an element. Okay? So if you look over to your right, students in person, and you look at that big chart over there, periodic table, which you guys will have a paper copy of that you'll use every single day the second semester. Anything on there is an element. Copper, zinc, gold, platinum, silver, sulfur, phosphorus, silicon, chlorine, oxygen, nitrogen, carbon. Anything you read on there, that's an element. If it's not on there, it's not an element. If it's not an element, it won't be on there. Okay? So anything on that periodic table is an element. Those are the simplest building blocks of the universe. This little picture right here, do you guys see how every single atom is exactly the same? It's a little gray circle. These are all gray circles, okay? Every single one, doesn't matter where you circle them, boom, boom, gray circle, gray circle, gray circle, gray circle, gray circle. No matter what I grab out of that box, I'm going to get a gray circle, no matter what I do, okay? So it's a pure substance, because every time I grab some out of there, it's the same. But even more than that, it's an element specifically, because they're all the exact same atom. They're all a gray circle. Now, we also have compounds, and I'll come back to this in a moment. Going back to my tree. So pure substances are either an element or a compound. An element or a compound. So a compound is similar to an element. It's just at least two of them. So when you take two elements and you stick them together chemically, now you've got a compound. Now you got a compound. So two elements, two little atoms stuck to each other, that's a compound. Or at least two of them, I should say. When atoms join, they lose their individual properties and they gain new properties. They lose their individual properties and they gain new properties. Let me show you some examples of this. You don't have to write all these down. How about you write down NaCl and H2O. Those are a couple of good ones. Okay. Now notice, when I grab something out of this box, okay? When I grab something out of this box, no matter what, I'm going to get a Mickey Mouse looking thing. If I grab a big gray atom, I will get a big gray atom and two white atoms. If I grab Mickey by his ear, one of those little white circles, I'm going to get two white atoms and one gray atom. No matter what I grab out of this box, it's going to be the same. So it's a pure substance, but are all these atoms exactly the same? No, I have some gray atoms and I have some white atoms. Okay, the little tiny white atoms are Mickey's ears. The gray atoms are his little face. So that's why this is a compound and not an element. This could be H2O, for example, because you have two smaller atoms attached to one bigger one, like the two H's and one O. Yes, ma'am.
So if we mix the sulfur, if we mix the sulfur with another dry chemical element, would it immediately do that if we mix stuff like that? Would all of it?
Oh, that's a great question. Some elements will react with each other and chemically join, and some won't. And we're going to get into all that coming up. That's a really good question. Sometimes I will, sometimes I won't. Hey, by the way, here's an example of two elements having their individual properties and then they change. Sodium, so Na stands for sodium, Cl stands for chlorine, okay? Sodium by itself is a shiny metal that if it ever touches water, it explodes. I'll actually do that I'll do that as a demonstration for you guys down the road here. Chlorine is a yellow-colored gas used in chemical warfare to kill people. So we have a shiny explosive metal, deadly yellow gas. When you put those two things together, you know what you get? Salt. As in like the salt you eat. As in the salt you have to have in your system or you'll eventually die. So explosive shiny metal, deadly yellow gas, salt crystals that you have to live. So you see how you have two individual elements and we put them together they make a third completely different thing with totally different properties. That's what I'm talking about, how they lose their individual properties. So a little NaCl, sodium chloride, NaCl. That's what I sometimes say when I'm being a dork. NaCl. All right. So with our tree so far, if you have a pure substance, everything in the box is the same, quote unquote. is either an element or a compound. But we're going to add to the other half of the tree, we're going to talk about mixtures. Okay? Mixtures. So if it's not a pure substance, it's a mixture. If it's not a pure substance, it's a mixture. Two or more substances are mixed together but not chemically joined. So when you put two things in the container, they're not chemically joined, so they're still the same individual properties. That's a mixture. They retain their individual properties. So this isn't like a shiny explosive metal and a yellow deadly gas coming together to make a white crystal. Okay? The two things in a mixture, they retain their properties. So, for example, think about Chex Mix. You have a mixture of a bunch of stuff in a Chex Mix, but at the same time, the little square Chex, they taste completely different than the brown rye chips, right? They maintain their individual properties, even though they're all mixed together. Sugar water is a mixture. Okay, I have pure water right here. If I go ahead and I just scoop in a teeny bit of sugar, now this is a mixture. Now the sugar and water have not chemically joined in any way. This is still just water and sugar in here. But now the sugar molecules are surrounded by water molecules. If I took a sip of that, I would taste the water and I'd also taste the sugar, okay, because it's still just sugar and water. They're just in the same container now, mixed up, okay? They haven't chemically joined. They're not all of a sudden a bright yellow gas or something. Uh-huh.
So, can they chemically join by being mixed at like different heats and temperatures? Because like if you put in like tea and you put some like sugar in your tea or like something that is also a liquid like honey, could it chemically join if it was also the same state?
That's a great question. In that particular case, we're still talking like with hot tea, like I can't see the honey anymore. What the heck? The honey's just sort of mixed in there. Okay, so that would just be a mixture. But there are other chemical reactions where when you put two things together, nothing happens. But if you heat them up, then all of a sudden something happens, and you do get a chemical reaction. So that's good. Yeah, Gabby.
You know, yes, I want to know.
Want to know about chocolate milk? It's like my favorite drink of all time.
Yeah, like if you have enough and you pour chocolate and roll it down.
That is a great question. Okay, so the question is, if you put, Nesquik chocolate powder in the milk, okay, you mix those two together, what is it? That's still just a regular old mixture because, well, it's going to be a mixture no matter what, let's say, because you have more than one thing in there, okay? But if you think about it, you still taste the chocolate, you still taste the milk, so that is just a nice mixture. They're not chemically joined in any way, okay? We could separate those two, unlike a pure substance where you can't separate it. We could still separate those two if we really wanted to. That's great. Really good questions. I love it. So sugar water is a mixture, even though sugar by itself is a compound and water by itself is a compound. You put them together, all of a sudden you have a mixture. When you have more than one thing in there, you got a mixture. Okay? You have more than one thing in there, you got a mixture. Now, if I go back to my tree real quick, mixtures split off into two categories too. The first one is called a homogeneous mixture. A homogeneous mixture. This word right here. Homogeneous. The word homo means same. It just means same. Okay? Genius means look. So this, in other words, it's saying it looks the same throughout. When you look at it, it looks exactly the same. Mixtures that look the same throughout. For example, this sugar water right here. If I look at the bottom versus the top versus the middle, I mean, it looks the same throughout. This is a homogeneous mixture. A key word that you guys will probably say on your test someday when I ask you about this is the word even. You'll say it's evenly mixed. So the sugar and the water are evenly mixed in this little beaker. You can't see anything different. It looks the same no matter where you look. If I were to take a sip of this, which I would never do because this is not food glassware, every sip would taste basically the same, okay, because the sugar and the water is evenly distributed. This picture right here, it's a little hard for you guys to see, but there are actually some white atoms mixed around in these gray atoms. This is a white atom, white atom, white atom, white atom, white atom. You see how they're kind of evenly mixed throughout? This would be a homogeneous mixture because those white atoms are mixed evenly throughout the gray atoms. It doesn't mean you have the same number of white atoms and gray atoms. Just as long as they're mixed evenly, we're good to go. The other kind is heterogeneous. Hetero means different. Genius still means look. So this means it looks different. It looks different. Going back to the tree for a quick second. So we have homogeneous there. We have hetero there on your tree. So it looks different. And I'll go back to the tree if anyone ever needs me to. Mixtures in where you can see the different parts. You can see them. You can see those different parts. They're easy to visualize. They're easy to visualize. You have more than one type in the mixture. So, for example, these two pictures here. Do you see how you have these highlighted big chunks of atoms? You can really see those in the mixture, okay? Those aren't hidden throughout. You can see the different parts. Or, for example, you have all these white atoms on the bottom and all these gray atoms on the top. They're in the same container, so they're a mixture, but they look different. They look different when you look up top versus the bottom. That's heterogeneous. Here's a perfect example. I'm holding a bottle of baby oil and pink water. Guys see that? See how the baby oil is sitting on top? The pink water's on bottom, right? This is a heterogeneous mixture because it doesn't look the same throughout. If I were to ruin this nice little visual and go like that, I'm mixing up the baby oil and the pink water. What kind of mixture is this now? Homogeneous. It's homogeneous, right? Because you can't see the different parts. If I let this sit for the rest of the class period, they will separate back out. And in fact, if you look at the very bottom of that, you can see a little layer of pink water already starting to form and the clear baby oil starting to form at the top. Hey, quick question. Just going back to density. If the baby oil is sitting on top of the water, what is that? What do we know about baby oil? It must be less dense. Specifically, it must be less than what? 1, right? Because water's got a density of 1. So the baby oil must have a density less than 1. Boom. That's what we're talking about. That's what we're talking about. So that brings us to our little worksheet here. So on this worksheet, here are the things that you're trying to do. You're basically trying to travel down the tree. So the first question is it a pure substance or is it a mixture? How do I know if it's pure, Mr. P? I sometimes think everything. You don't have to write this down. In the box is the same. Let me show you what I mean by that. So if you take a look, it says question 1, are there mixtures that are present in line A1? Well, let's take a look-see. If I close my eyes and grab something out of A1 box, or the box A1, let's say I grab a black atom right here. What will I pull out in total? 1 black atom and 1 large white atom. What if I grab the white atom right here? I'd pull out 1 black atom and 1 large white atom, right? No matter what I pull out of that box, it's always going to be the same. So is that a pure substance or a mixture? Pure substance, right? That's a pure substance. Now, so we know that we're on the left side of that tree. So we're on the pure substance side of this tree. Okay? But here's a question. Are all of those atoms exactly the same in there? I don't think so. There's a large white atom, but there are also small black atoms. So they're not all the same. So is this an element?
No.
No. What would it be? A compound, right? Because you have more than one element stuck to each other. So you're just sort of working your way down that tree. And sometimes the question doesn't require you to go all the way down the tree. It just wants you, hey, is this a mixture of pure substance? You don't have to go all the way down the branches, okay? But that is a general idea. So I would use that tree visual, kind of work your way down for the different questions. So if I was starting to answer this question, like, oh yeah, A1, not a mixture, so no way. Because no matter what I grab out of there, it's always the same. If you're watching from home, the answer key is below. If you're in person, it's the peach sheet on your desk. And I'll come around and see if anyone has questions. Got about 10 minutes. Go get them, nerds.